Now we're going to talk about intensity of sound waves. So in our previous experiment where we have the piston where we apply an additional force delta P times area, we're delivering some power to this gas. And how much power is delivered by the piston? Power delivered by the piston we can calculate uh, by looking at the force and the velocity of the piston. So we're applying this force F. Remember, force dot product with displacement is work. Force dot product with velocity is the power. It is dw dt. So if I write for this power is equal to the force that I'm applying, the net force that I'm applying here is delta P times the cross-sectional area A in I hat direction, dotted with the velocity of the gas molecules, that is d dt of displacement s xt in I hat direction. So I'm going to get for the pressure part, the pressure wave is given as delta P max sine kx minus omega t, and now I also have the area A here, and then I have the time derivative of S max cosine kx minus omega t. So this will give me for the power power is equal to area times delta P max sine kx minus omega t. Then from the derivative I'm going to get a minus omega, but the derivative of cosine gives me a minus sign, so the minus signs will cancel, so I will end up with omega times S max sine kx minus omega t. So this is going to be equal to area times delta P max delta P max omega S max sine squared kx minus omega t. Now I want to describe this purely using the displacement, not the pressure. I know that the pressure is related to displacement amplitude is bk S max, and B is equal to V squared times rho K S max, and K is, remember, omega divided by V. So I have rho V omega S max for delta P max. So this will be equal to A rho V omega square S max square sine square kx minus omega t. Now I would like to know the time averaged power delivered, average power in one period. So in one period of the oscillation, how much power do I deliver? So this is going to be average power is 1 over the period integral of power dt, and if I fix the position at x is equal to 0, I'm just taking a picture of this. At x is equal to 0, I wait for one period and see how much power I'm delivering to the system at x is equal to 0. This will be equal to 1 over t a rho v omega squared s max squared integral from 0 to t sine square kx sine square minus omega t dt. And because I'm taking this square, if it's a minus omega t or plus omega t, doesn't matter. So I can just replace this minus with plus, because sine of minus omega t is minus sine omega t, but its square will give me the same answer. So this part we can evaluate separately. So 1 over, including this period, 1 over the period integral from 0 to t sine square omega t dt is 1 over the period integral from 0 to t 1 minus cosine 2 omega t over 2 dt. So this will give me 1 over 2t. The integral gives me a t, and then I will have minus 1 over 2 omega sine 2 omega t evaluated between 0 and the period. Evaluated at 0, sine will give me a 0. Evaluated at the period, the sine 2 omega t will become sine 4 pi, because omega, remember, is 2 pi divided by the period. So this part is going to give me 0, and this part is going to give me a t, and therefore I will end up with 1 over 2. So basically, I find that the average power I'm delivering in one period is 1 over 2 rho v omega s max squared times area A. Now we define the average power per unit area, averaged power per unit area perpendicular to the wave is defined as intensity. So what is intensity? Intensity is the average power per area. So this will be equal to 1 over 2 rho v omega s max squared. So that's one way to describe the intensity. I can also write the same equation using instead of S max, delta P max. All I have to do is to remember between the relationship between them. So I can substitute for delta P max is equal to BK S max. B is V squared times rho density. K is omega divided by V S max. So for delta P max, I can write rho V omega S max. Therefore, the intensity becomes 1 over 2 rho V, and instead of omega S max, I write delta P max divided by rho V squared. So my answer will be 1 over 2 delta P max squared rho V. So this is the intensity written in terms of delta P max. So I find that the intensity is proportional to S max squared or delta P max squared. It's proportional to the amplitude of the wave squared. If the sound wave propagates in all directions, if I have a point source, there is a point source of sound waves, and the waves are propagating in all directions. Now these arrows that show me the propagation direction of these waves are called rays. So these are rays, and when I look at the maxima and minima as I go away from the source radially outward, for example, I will find that when I'm equidistant from the source in this location, I have all of the maxima are lining up along this circular arc here, in which I have a constant phase relationship. So all such points in space that are equidistant points from the point source where I have the same phase relationship between the waves. So these are all maxima occurring here and maxima occurring here. These are all spherical surfaces. And these shapes are called wavefronts. And because I have all wavefronts are spherical surfaces, the type of wave I obtain here is called a spherical wave. Spherical wave. The wavefronts are spherical surfaces. Okay, so in that case, I'm going to see that the intensity that is equal to the average power per area is going to be average power divided by the area of these spherical surfaces. So if I'm at a distance r from the source, it's going to be 4 pi r square. That's the surface area of a sphere. So the intensity for the point source will be changing with radial distance like this. So this is for the point source. Sound intensity decreases as 1 over r squared, where r is the distance between the point source and the point of interest where I'm trying to calculate the intensity of the sound. Let's take a look at a few examples. The faintest sounds the human ear can detect at a frequency of 1000 Hz correspond to an intensity of about 1 10 to minus 12 watts per meter square. So at frequency of 1000 Hz, we have the minimum intensity we can hear is 1 10 to minus 12 watts per meter square. That's called threshold of hearing. The loudest sounds the ear can tolerate at this frequency correspond to an intensity of about 1 watts per meter square. So that's the threshold of pain. Determine the pressure amplitude and displacement amplitude associated with these limits. And I know that the density of air is 1.2 kilograms per meter cube. The speed of sound in air is 343 meters per second. So the intensity is related to the pressure amplitude and displacement amplitude. Intensity is average power per area, and it is given as 1 over 2 rho v omega S max squared, or it's given as 1 over 2 rho v delta p max squared. And the way to remember this is basically to find an analogy between this one and waves on a string. So remember, for waves on a string, we have the energy carried in one wavelength is equal to 1 over 2 mu lambda omega times amplitude squared, and the power was given as 1 over 2 mu v omega a squared, and here mu is replaced by density. V on the string square root t over mu is replaced by square root b over rho. Omega is the same omega, amplitude is S max. So with this analogy, I can see the intensity as a function of S max. And the relationship between these two come from the fact that delta P max is rho v omega S max. Right. So I want to know the pressure amplitude and the displacement amplitude. So the first thing I have to do is let's start with the pressure amplitude. Delta P max is going to be square root 2 rho v times intensity I. So for the threshold of hearing, I minimum 1 times 10 to minus 12 watts per meter square. I have the following delta P max. Delta P max is square root 2, 1.2 kilograms per meter cube, 343 meters per second, 1 times 10 to minus 12. So this will give me 2.87 10 to minus 5 newtons per meter square. That's called pascals, by the way. So it's 2.87 10 to minus 5 pascals. 1 pascal is 1 newton per meter square. That's the SI unit of pressure. And for maximum intensity, for 1 watt per meter square, I have delta P max is equal to square root 2 rho 1.2 343 times 1. That gives us 28.7 pascals. So these two will be the amplitude of pressure, maximum pressure I will have in the sound wave. And the displacement amplitude I can also obtain. So basically the S max is equal to delta P max divided by rho v omega. So I can just calculate what rho v omega is, and if I substitute here 2.87 10 to minus 5 for threshold of hearing divided by 1.2 343, omega is equal to 2 pi f, so it is 2000 pi radians per second. So it's going to be 2000 pi here. I will obtain an S max of 1.11 10 to minus 11 meters, and for the other one I will obtain S max 1. S max 2 is going to be 28.7 divided by the same thing, 1.2 343 2000 pi, and this will give me 1.11 10 to minus 5 meters. So So I have found the corresponding displacement and pressure amplitudes. Let's look at one more example. A point source emits sound waves with an average output power of 80 watts. Find the intensity 3 meters from the source. So for part A of this problem, intensity is average power divided by the area, and this is a point source. Therefore, I'm going to have spherical waves emanating from the source, and at a radial distance r, I will have average power divided by 4 pi r square is the intensity. So I want to know the intensity for 80 watts, 4 pi 3 squared, 9. So this will be 0.707 watts per meter square intensity. Find the distance at which the intensity is 1 times 10 to minus 8 watts per meter square. So the distance r I can find using this relationship, average power divided by 4 pi r square. So r is equal to average power divided by 4 pi I square root. So this will be square root of 80 divided by 4 pi 10 to minus 8. So the answer is 2.52 10 to 4 meters. So I have used the spherical wave relationship. Intensity is equal to average power per area, but that area is the area of a spherical surface, 4 pi r square. To calculate the intensity, then for a distance where I can find the intensity of sound to be 1 times 10 to minus 8 watts per meter square, I have found that distance to be 2.52 10 to 4 meters. Now remember, the threshold of hearing was 10 to minus 12 watts per meter square, so this is greater than the threshold of hearing. So this is a sound we can hear